For centuries, we believed we understood the force that holds the cosmos together, the same force that makes an apple fall to the ground, that keeps the moon in its course around the Earth, that anchors galaxies in their majestic spirals. We call this force gravity. But what if we are wrong about what gravity really is? What if the nature of the universe is even more subtle, profound, and surprising than we ever imagined? At the end of the 17th century, in an England of green fields and effervescent ideas, a solitary man was about to forever change our understanding of the world. Isaac Newton, the son of farmers, born prematurely during a storm, grew up to become one of the greatest thinkers in human history. In 1687, he presented to the world his masterpiece, the Principia Mathematica. In it, Newton proposed a simple, elegant, and revolutionary idea: that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Imagine an apple falling from a tree. For Newton, it was not just the apple and the ground. It was the entire Earth attracting the apple, and the apple, in turn, also attracting the Earth, albeit almost imperceptibly. This force, according to him, was instantaneous, acting at a distance without delay. If the sun suddenly disappeared, the Earth would immediately feel this absence, deviating from its path around the void. Newton's law fit perfectly with the data of the time. The planets obeyed, the moons danced to its rhythm, the tides bowed to its will. For centuries, navigators, engineers, and astronomers trusted these equations, even to send men to the moon centuries later. It was a description of the universe as practical as it was powerful. But time advances, and with it, human curiosity. In 1915, another genius born in German lands was about to lead humanity to an even deeper revolution. Albert Einstein, with his restless gaze and incandescent mind, did not see gravity as a mysterious force acting at a distance. For him, Newton's explanation was incomplete, a useful approximation, but not the fundamental truth. Einstein proposed something almost unimaginable. Space and time were not rigid, immobile entities. They were flexible, shaped by the presence of mass and energy. Gravity, then, was not an invisible force pulling objects, but rather the curvature of the very fabric of space-time. Bodies fall not because they are pulled, but because they follow the curves and folds of this cosmic geometry. Imagine a stretched trampoline. If you place a bowling ball in the center, the surface curves. Now, roll a small marble over this trampoline. It will not be magically pulled by the bowling ball, but will follow a curved path, guided by the deformation of the surface. Thus, Einstein taught us to see the universe as an elastic tapestry where masses distort space-time and, consequently, determine how bodies move. This new vision brought with it extraordinary predictions. Einstein predicted that time is not absolute. It passes more slowly near large masses. The light from the stars, when passing close to the sun, should bend, a subtle but detectable effect. In 1919, during a solar eclipse, astronomers confirmed this prediction. The light from the stars really bent as it passed through the solar gravitational field. It was the consecration of the theory of general relativity. In everyday life, for small speeds and modest masses, Newton's equations work perfectly. Throwing a ball, launching a rocket, predicting the return of a comet, all of this can be described with Newtonian accuracy. But in extreme environments where gravity is overwhelming or speeds approach that of light, Newton's theory fails. Near a black hole or at the edges of the universe, only Einstein's equations can handle the task. General relativity also predicts previously unimaginable phenomena. Gravitational time dilation, where clocks near large masses run slower. The existence of black holes, where space-time curves until collapse. Gravitational waves, ripples in the fabric of the universe created by colossal events, such as the merger of neutron stars. In 2015, 100 years after Einstein's theory, humanity detected these waves for the first time, once again confirming the genius of this cosmic vision. But if Einstein was right, why do we still teach Newton in schools? The answer is simple. Newton's theory, although limited, is extraordinarily useful and simple for almost all everyday purposes. Building bridges, launching satellites, predicting eclipses. It provides precise and easy-to-calculate answers. It's like a city map. It may not show every detail, every crack in the sidewalk, but it guides us effectively. General relativity, although more accurate, is complex, requires advanced mathematics, and often goes beyond what is necessary to solve practical problems. Moreover, not even Einstein held the final word. When we look at the infinitely small world of subatomic particles, his theory begins to fail. In the quantum realm, the laws of gravity and space-time become blurry, disconnected. The search for a unified theory that reconciles general relativity with quantum mechanics is today the holy grail of physics, a challenge that intrigues the brightest minds of our time. And what remains of Newton in Einstein's universe? What remains is his boldness, his ability to ask, to doubt, to seek explanations for the ordinary. Why does the apple fall? A simple question, but capable of triggering an intellectual revolution. Newton gave us the first language to describe the invisible forces that keep the stars in the skies. He built the foundations upon which generations of scientists have raised new theories, ever more comprehensive and profound. By rewriting the laws of the cosmos, Einstein did not erase Newton. On the contrary, he acknowledged that, if I have seen further, it is by standing on the shoulders of giants. The progress of science is a journey of many steps, many minds, and many questions. From the English orchard to the edge of a black hole, we keep falling, not toward the ground, but toward an ever deeper understanding of the truth. In the end, the question remains, is gravity a force, or is it the very form of reality? Is the universe a tapestry of invisible forces, or a malleable stage where space and time dance to the tune of matter? Each answer brings us closer, but also reveals new questions. The quest for understanding is endless, and it is precisely this that makes science so fascinating. The journey of knowledge is made up of questions that bend the mind and answers that reshape our world. It doesn't matter if we are watching an apple fall or probing the edges of space-time. Curiosity always drives us forward. Newton and Einstein, each in their own way, taught us to look up, to question, to imagine. And as long as there are questions, there will be new discoveries and new wonders waiting to be revealed. Therefore, from the serenity of an English orchard to the vastness of an expanding universe, we continue to explore, to learn, to fall, deeper and deeper, closer and closer to the heart of the mystery. Because understanding the universe is not the task of a single genius, of a single theory, but of all of us, together, looking at the sky and daring to ask, why? And so we continue this journey, with Newton and Einstein as our guides, remembering that true power lies not only in the answers, but in the courage to question, to imagine, to dream. The cosmos awaits, and we move toward the unknown, ready to challenge old truths and embrace new ones. After all, it is curiosity that drives us, and just like gravity, it keeps us together, bound to this extraordinary universe of possibilities.